Okay, recording is rolling. So, welcome to Monday, December 13th. Hope you guys had an awesome weekend. Thank you, everybody, for turning in your rotational dynamics quiz. I will get those graded. What just went out? So, that go out. I'll get those graded as soon as I can. And once I have them all in, which will hopefully be really soon, then I have all the solutions ready to post. And I will get these back to you so that you can use these to study if you need to. All right, so back on Thursday, Friday, we were looking at the kinematic motion and also forces for that part of the review. All right, so let's start with some warm-up problems related to those, and we'll go on to the next part of the review. Suppose you have a question like this. Take a ball, edge of the cliff, throw it straight up with some V0, and it sort of comes down crashing in this valley down here. Like my little dusty mushroom problem. So if you look at this velocity versus time graph, could you guys interpret, say, different things from this graph? I see from the point of release to where it landed, there's 4 seconds. The fact that you threw it upwards and eventually comes downwards, there's a change in direction. Do you guys see it starts with a negative velocity and it's a positive velocity? So it looks like down is the positive direction. Hey, what's the slope of this graph equal to? Acceleration, which looks like up 10 meters per second divided by 1 second. Yeah, that's 10 meters per second squared. So this cliff is almost certainly on Earth, right? Because that would match Earth gravity. Okay? But what about this question? What's the height of the cliff? Okay, so I'm going to tell you guys 3 different ways to approach the answer, and then you guys can get it from there. So one way, what property of this graph could answer that question? Area. Yeah, you guys are thinking area, right? And so here's one way. You can find the area of that big triangle, the area of the small triangle, and subtract those, right? They would subtract from each other. Think that little area right there, that represents just like this bit here, like move it up. And then think about that. You think, well, maybe it goes up and it comes back down and all that washes out. It has nothing to do with the height of the cliff, just everything after that. So if you wanted to, you could look at that part and say, hey, those 2 triangles wash out. And then I'm left over with this trapezoid, or just this trapezoid could tell you the height of the cliff. Okay? And here's a third way you could do it. If you know this is your V0, you know this is your acceleration, the slope of this line is acceleration, and here's your time interval, 4 seconds. Look at this right here. The height of the cliff, this h is this x, right? Is the initial velocity times the 4 second time interval, plus 1/2 at squared. You did that way too. There's 3 different ways you can get that answer. Okay? Next questions. Oh, look at all these. So let's take a look at that ball. Now, I know the graph we were just looking at, we were assuming a vacuum, and you know that because the acceleration is constant. But now let's change that assumption. Let's bring in air drag. Look at that. I got a 3 kilogram ball. It weighs 30 newtons on Earth. Let's say it picks up to 50 newtons of air drag. First of all, what's the net force on that ball? 15 newtons. Isn't the acceleration is net force acting on some mass. Do you guys see 30 newtons minus 15 newtons of net force acting on 3 kilograms of mass? Wouldn't that be, let's see, 15 divided by 3 is 5 meters per second squared? Is that true? Okay. Atwood. So I see this whole thing's going to accelerate clockwise. Okay. Now, you guys should be able to solve all these in terms of variables also, but I've got some numbers, so let's just stick with that again. Okay. Do you guys see 30 newtons of weight pulling clockwise and 20 newtons of weight pulling counterclockwise, right? M times G. Okay? So go back to Newton's second law of motion. Acceleration is net force acting on some total mass. Okay? Do you guys see 30 newtons clockwise minus 20 newtons counterclockwise, all acting on 3 kilograms plus 2 kilograms worth of inertia? Okay? See the difference in those weights. Just think about the motion of this outward. If these had been the same mass and the same weight, then the numerator would wash out to 0, and then it wouldn't accelerate at all. You guys know that from doing this lab. I've got 10 newtons of force acting on 5 kilograms of mass. That looks like 2 meters per second squared. Okay? And all these double elevator outwards should be bounded somewhere between 0 and pure free fall. 0 if they're 0 meters per second squared if they're the same mass. Pure free fall if you put all the mass on one side. Okay? How about this guy right here? What's the tension in each supporting cable? Okay. First of all, what is this weight equal to? I see the mass is 8 kilograms, but how much weight in newtons is pulling down? 80 newtons. Okay. How many of you guys are looking at that 37-degree angle thinking from the vertical? Right? Thinking, I know why 37 degrees. That's going to set up some special geometry, isn't it? Because I want you guys to see the big picture of this. I'm going to make a free body diagram of this point right here where all the strings come together. Now it's a little short rope. Of course, the tension in that little piece itself would be 80 newtons. But what about the tension in each one of these supporting cables, right, once it splits? Right? Let's take a look. Okay, so we've got 80 newtons pulling straight down. Okay. Oh, back up a little bit here. Okay. All right, then at 37 degrees from the vertical, 37 degrees from the vertical, there's something pulling up to the left, and at 37 degrees the other way, say clockwise from the vertical, okay, there's a tension pulling up to the right. Now, just based on symmetry, you guys see that these tensions are going to be the same. So I'll just go ahead and label them each T. Okay, don't worry about subscripts because they have to be the same thing. Okay. You guys remember the way you're going to approach this is to, there's two equilibrium conditions we're thinking about. One is that the sum of the forces in the x direction is 0. The other is that the sum of the forces in the y direction is also 0. The sum of the forces in each direction is 0 since we've got a 2D plane. Okay? Now let's take these tension forces and split them into components that align with this Cartesian system. Okay? So the one pulling up to the left, well, it's kind of pulling up, kind of pulling to the left. One pulling up to the right, well, it's kind of pulling up, kind of pulling to the right. Okay? How much? Well, it depends on that angle. Okay? Let's think about components. Okay? So remember, each one of these conditions, right? So some of the forces in the x equals 0, that just means the left part equals the right part. Okay, so but look at this one right here. The y direction force, all the vertical stuff has to also 0 out. So if you got 80 newtons down, doesn't it have to be collectively 80 newtons up? And that's split two ways. So how much is just this vertical component right here? 40. I got 40 newtons up here and 40 newtons up here. Right, 40 and 40. Okay. Right. Now here's where the geometry kicks in. Who knows why I picked a 37-degree angle? Because that would make a what triangle? 3, 4, 5. 3, 4, 5. Yeah. Now, if it was any other angle, you could say, well, this tension based on this vertical component, that's a cosine relationship with that angle, whatever it is. In this case, like cosine of 37 degrees is 40 newtons divided by tension. You solve for tension. Okay. But the fact that you guys know the 3, 4, 5 geometry means you can get the answer right away. This tension is equal to how much? 50 newtons. Yeah. You guys know what's going on. 50 newtons. 50 newtons. Okay. If they were each exactly vertical, it'd be 40 and 40. So balance out it's 80. But they're kind of on an angle. The more you spread them out, the more the tension's going to build up. I had you guys do a lab way back in the day with spring scales. You guys saw that. Okay. This guy right here, I didn't write the question, but the question is going to be, if this block is sliding down at constant velocity, what coefficient of kinetic friction would you need between the block and the surface to make that happen? So let me blow that up here, and then write out this question to take you guys through that. So what coefficient of kinetic friction, say between the block and the surface, if this is mu sub k, so between those two surfaces, okay, so that block slides down with constant velocity. Okay, so go back. And it draws picture a bit on the left, so I think I can write all the stuff I want to write in this margin on the right. Okay. So we got this block. Okay. I'm going to give you guys a 37-degree angle again because I want to set up some pretty straightforward geometry so that your brain can crunch everything that's going on. And then, of course, you can do more complicated stuff with the equations once you know how to do stuff. Whenever you guys see an incline, you guys see plenty of these, then you guys know to introduce a Cartesian system that runs parallel and perpendicular to that surface. Okay. This block is supposedly sliding with some constant velocity, okay, which if there was no friction would not be possible, right? If there was no friction, it would be accelerating. if this was like an air hockey table, an air hockey puck, and let's say you lose the game, you're like, lift up the table, it's going to accelerate down. Or one of the very first labs you guys had with the Hot Wheels cars, those were accelerating. Right? We did all the graphs and stuff with it. So constant velocity, well, you would need some particular, some exact coefficient of friction between this surface and this surface to make that happen. I wonder what that's going to be. So we need a free body diagram. You guys ready for a free body diagram? Now, if you guys get this as an FRQ on the AP 10, which you totally could, this could be an FRQ. Okay. And they say, draw a free body diagram. You guys are going to draw exactly 3 forces. Okay. You guys are going to draw a weight. I'll call this mg. You guys are going to draw what other forces? Normal force plus F sub n, normal force, and also a what force? Friction. F sub upper. Oh, and notice how I made the friction opposite of the direction of motion. Okay. Oh, let's do this. I'm going to, in blue ink, give you guys some numbers, like this 37-degree angle, and then in red ink, maybe I'll just leave that as variables. Let's call this mass 5 kilograms. Okay, so 5 kilogram block, which means it weighs how much? 50 newtons. Okay. Now, I'm going to split this into components, but be careful with splitting into components because, for an AP FRQ, you just draw that and walk away. Right? If you really have to draw components, then make sure you dash them. Otherwise, AP counts that as like double counting. Okay. So the weight of the block, this 50 newtons of weight, is partly pushing the block into the incline, and it's partly pulling the block along the incline. And those are the 2 components I'm going to do. Do you guys see how I'm holding the ruler parallel to the surface? Right? Parallel to the surface to draw this parallel component. Okay. You guys get practice doing that? So parallel, right? You guys see parallel lines? Okay. So it's that way. Okay. This is still some angle theta, and then I'll tag on the 37 degrees. Okay. In general, this component right here is mg, what sine or cosine of the angle? Sine of the angle. And this one, of course, would be g cosine of the angle. Okay. And then in blue ink, let's throw in the numbers. Now you guys know the geometry. You guys see this is a 3, 4, 5 right triangle. I got 50 newtons of weight, which makes this leg is equal to what? 40 newtons. Or no, I'm so sorry. This one's 40 newtons.
Yeah.
And this one's how much? 30 newtons. That's what I meant. Okay. That's it. All right. This normal force must be equivalent to this component right here. So that's also equivalent to mg cosine theta. And you guys see, of course, that's just going to be also 40 newtons according to these numbers. Okay. Right, now here's where it's this friction force. Right. The fact that I said constant velocity is a condition of equilibrium, or it's one possibility of equilibrium. Okay. And that means that this friction force must be exactly balancing this right here. Isn't that also true? Okay. So in general, it's mg sine theta for constant velocity or equilibrium. Even if the block was just stuck on the surface, it would still be equilibrium. It would still be true. Okay. And then for the numbers, how many newtons of force? You guys see 30 newtons of force, so that it exactly balances out this guy. Okay, you guys that? Okay. Right. So question is, what's the coefficient of kinetic friction? Coefficient of kinetic friction. Okay. You guys have a formula for that. In fact, it's on your AP equations. Do I have that in reaching distance? I think I do. Let's see if I point it out to you guys. Oh, I am. I know it's right in front of me, and I'm being blind about this. Here it is. Okay. Friction force is, well, it says less than or equal to coefficient of friction times normal force. The inequality is if it's possibly static, but you can say equals if it's kinetic. Okay. So rearrange that a bit, and we're going to get friction force compared to normal force. That's the coefficient of friction, right? Okay. So in terms of the variables, I've got coefficient of friction is friction force is mg sine theta. Normal force is mg cosine theta. Okay. In terms of the numbers, just down here, it's 30 newtons compared to 40 newtons. I see that? Okay. So two perspectives, variables, numbers. Okay.
So basically, the coefficient of friction is just tangent theta.
Exactly. That's exactly where this is going. Tan theta. That's a good little tidbit to know. Yeah. If you ever have this exact scenario, sliding down constant velocity, that is true. Yeah. That. And then let's see, in terms of the numbers, that would be 0.75, right? Let's see if I'm lying to you guys or not. Okay. Now you guys know 37 degrees is a little bit rounded for 345. It's actually like 36.9. So this won't be exact, but it should be really, really close. Let's see how close. Tangent of 37 degrees. I hope this is 0.75, or really close to it. 0.75. Okay. Okay. There's it. All right. So a couple more force conceptual questions, and then we're about to move on to momentum. Large truck, small car traveling at the same speed have a head-on collision. Bam! The vehicle to, let me pause right there. Do they both experience the same force in that collision? Same force? Yep, that's Newton's third law of motion. Okay. But the actual question here is the vehicle to undergo the greater change in velocity, like have the greater acceleration. And that vehicle is which one? The small car. Yeah. So same force, but different accelerations because different masses. Okay. Which vehicle would you be safer driving? Yeah, the large large truck. Okay. Because you personally inside would accelerate less, so you'd be a little bit safer. Two people pull on a rope, tug of war. Each person pulls with 400 newtons of force. What's the tension in the rope? The 400 newtons. That's the answer. Okay. So this guy, rope. Okay. Let's look at a point close to this guy's hand right here. Okay. He's pulling to the left with 400 newtons of force, and there's a tension the other way, pulling back with 400 newtons. This guy gets the opposite story over here. 400 newtons of tension, 400 newtons of pulling force. So everything's 400. Table tennis ball launcher is fired. Compared to the force on the ball, the force on the launcher is what? Spell this out. Say in table tennis ball launcher, in a few minutes they say something about a cannon. It's the same. I messed up that picture. It's the same principle though. Okay. So let's get a launcher. Ball. Okay. Now, whether this is a table tennis ball and a launcher or a cannonball and a cannon, it's the same physics ideas. Okay? That while this ball is inside the barrel, that there's some force on it this way. Okay? Guys, is there an equal and opposite force back on the launcher? There sure is. That's Newton's third law of motion. It's the same force, opposite directions. Okay? Some explosion going on the inside. But the next question, a table tennis ball launcher is fired compared to the impulse on the ball. The impulse on the launcher is, hey, impulse. That is a change in what? Momentum. Exactly. Change in momentum. I can write it this way. Delta P. Change in momentum. Delta P. Okay? And there were two perspectives on this that you could push all into one equation. Change in momentum. Well, you guys remember momentum was mass times velocity, right? And so change in mass times velocity. Okay. Now, you could create a scenario that involved changing mass, like if you have like a conveyor belt, something was being dropped on or something. But almost always it's you have constant mass and change in velocity. So I'll write it that way. Mass times change in velocity. Okay. But then if you think about it, well, change in velocity, that means there must be an acceleration. If there's an acceleration, there must be a net force. So what was the other half of this equation? Mass times change in velocity is equal to what times what?
Average force over time.
Average force times time. Exactly. Yeah. Like they said, average force too, because if you had a variable force, which we'll look, I've got a problem lined up in a few minutes. You would want the average force. Right? If you guys saw a force versus time graph, wouldn't the impulse be the area under force versus time? Something to do with force times time. Right. Okay. So if the force is the same, and the time that the force acts for is the same, then isn't the impulse also the same? Yeah. So impulse is also the same. Now you might be thinking, well, I can see this cannonball going really fast to the right, and the cannon itself, it has a recoil speed. It goes back kind of slow. But that's because the cannon has so much what? So much mass, so much inertia. Those are both great answers, right? Either mass or inertia. Okay, so same impulse, same force for the same time, but different masses result in different changes in velocity. Yeah, right. And that's exactly the next question. Cannon recoils from launching a cannonball. The speed of the cannon's recoil is small because the cannon has so much more mass than the cannonball. A piece of putty with 2 units of momentum strikes and sticks to a heavy bowling ball that is initially at rest. After the putty sticks to the ball, both are set in motion with a combined momentum equal to. Oh, get some putty here, flying in. It's going to stick to this ball. Let's say it was originally moving in with 2 kilogram meter per second. Are they both going to roll off with a combined momentum of 2 kilogram meter per second? That would be conservation of momentum, wouldn't it? For an inelastic collision, because they collide and stick. Okay. You know what question I should have left on here that somehow got cut, but I wish I hadn't cut it? Was what if you have this scenario instead? Instead of a piece of putty going colliding inelastically, what if instead you have a bouncy ball going boing, colliding off elastically? Let's say it's also coming in with 2 kilogram meter per second, but it rebounds at like 1 kilogram meter per second. And since momentum is a vector quantity and it bounces back the other way, I'll even call it negative. Okay? That's what is the change in momentum of that bouncy ball? Do you guys see 3 units of momentum? Okay? Therefore, how much momentum does the bowling ball acquire and roll off with? About 3 units of momentum. Okay? In general, what delivers a greater impulse and also greater force? The bouncing elastic, or say closer to elastic collision, or the collide stick inelastic? What delivers more impulse? The bouncing collision. Yeah, anything that's closer to elastic. You guys see that right there? A 2 kilogram ball thrown at 3 meters per second. What's the momentum? And this is a gimme question here. Momentum is just mass times velocity. So if you have 2 kilograms, 3 meters per second, we're looking at 6 kilogram meter per second. Is that true? Okay. The next question is an energy and work question. So let me make sure I got all the momentum questions that I want to ask you guys. What if I got a couple of train cars, and I'm going to say 2 train cars collide inelastically? What is the post-collision velocity of the 2 train cars coupled together? So get a picture here. Got train car, let's say that the mass of this guy is 10,000 kilograms, and the mass of this guy is 20,000 kilograms. I'm going to have the small guy coming in with a velocity of, say, 30 meters per second. And let's give this guy an initial velocity of 0 meters per second. It's just sitting at rest. These 2 cars are going to, bam, collide together. And the fact that I said couple together, we are talking about an inelastic collision, aren't we? Collision. Inelastic collision. Okay. Whenever you see collisions and masses and velocities, okay, well, conservation of momentum, right? So that's going to be our approach. So sum of momentum before the collision equals sum of momentum after the collision. And before the collision, you had the first car moving at its initial velocity, plus the second car moving at its initial velocity. And then after the collision, well, coupled together, inelastic collision, that means they're going to make one giant mass, ma plus mb. They're going to roll off together with some common final velocity. And that's exactly what we're solving for. What is that final velocity? AP, far more often than not, if they have some collision, they almost always pick inelastic collisions. Because elastic, the math gets really crazy. You guys remember that because kinetic energy is conserved for elastic, but not for inelastic. Inelastic, all you have to do is this. It's really straightforward. Momentum plus momentum equals combined momentum. But boom. Let's pop in some numbers. Have 10,000 kilograms moving at 30 meters per second, plus, well, the other one was just at rest, so this whole piece just, whatever, doesn't add momentum to the system. It has inertia, though, and that's important for this side of the equation. 10,000 kilograms plus 20,000 kilograms, moving at some final velocity. Sure. Okay. Finish this off with some algebra. Take 10,000 times 30, all divided by 30,000. Getting a final velocity of 10 meters per second. There you go. That's the answer. And so, conservation of momentum, inelastic collisions. That'll probably be a really good multiple choice question on the AP exam right there. Here's a little bit different way to look at it. Some initial mass times velocity coming in, right? And then after the collision, sort of think of like the mass being tripled from 10,000 to collectively 30,000 kilograms. Sort of like the mass got tripled. Right? And look what happened to the speed. From 30 down to 10 meters per second. Well, it got cut into a third. 3 times the mass, a third of the velocity. That's another way to conserve momentum. If you think about it that way, a little bit different way to think about it. All right. Guys ready for a kind of a tricky question? Okay. You guys remember the baseball question? Here, I know there have been a lot of baseballs. Let me clarify that. Let's say you have a baseball. Has a mass of 0.15 kilograms. Okay. And it's being thrown towards the plate at, oh man, I have all my numbers ready, but make up numbers on the fly here. Let's say V naught of 30 meters per second. Okay. My numbers don't work out. I'll have to. We'll make this happen. Okay. Right, here's home plate. Right, there's a batter here. It's gonna bam hit this baseball back the opposite direction. Now I'm gonna give you guys a graph, and then based on that graph, here, maybe I'll set up some axes down here. I want to figure out what is the post-collision velocity of the baseball. Okay. Right, so ball was thrown at some speed toward the plate. Right. I'll set you up a graph. There's going to be bam, bat hitting the ball. It's going to knock it back the opposite direction with what velocity? Okay. Now I have not labeled the axes on this graph because I'm hoping that you guys know what axes I'm going to label these. Okay. This is going to be a what versus what graph. If we're talking about, let's see, collision between a bat and a ball. Ooh, collision probably something to do with momentum. Okay. If we're talking about momentum and the change in momentum of a ball, we're probably talking about impulse. We're probably talking about a what versus what graph. Force versus time, exactly. As on the AP exam, you will see a force versus time graph. I mean, there's no way they can't ask this question or something similar to it. Force versus time. Okay. And when you do see that graph, force versus time, you should, the gears in your mind should already be turning. You should already be thinking that what property of this graph is going to represent change in momentum. How about the area under the curve, right? And these graphs usually take this shape. They usually take like a classic triangle type shape. Okay? Not always, but I'll show you why they do. Okay? because we're talking about time and actually I should have labeled this milliseconds, but that's okay. I'll just put in really small time interval. Okay. Let's call this like 0.00, 0.01, 0.02. So I got 0 milliseconds, 10 milliseconds, 20 milliseconds. Okay. So really small time interval. And here's the story frame by frame. We got a bat swinging this way and a ball coming in this way. Right? Right? They just start to touch right here, and there starts to build up a force. Okay? Then at this moment, at the point of maximal force, we got the balls all maximum squashed. Bat's still moving this way, but the ball is changing its direction. Okay? And then in frame 3, now the ball has just left the bat right at this moment, and it's starting to fly back the opposite way. Okay? You guys see that? Okay? So all happens like bam, really tiny time interval. Okay? And usually that's how these work out. Right, now I'm going to throw, this is supposed to line up. Okay. I'm going to throw a maximum force on here and, okay, you know what? Actually, let me hold off on that because I want to make sure my numbers work out. I lost my notes somewhere, but okay. I'll show you how to solve this. Side thought here. Guys, see this maximum force? Maximum force? Do you guys think that the average force would be half of that? Like if you had a block of ice that was like a triangle shape, right, and you let this thing melt down and it was constrained by these walls, right, you think it would melt down into a rectangle like this? Oh, that might be like average force times time interval, like an impulse. The impulse is totally the area of this triangle. Call it delta P. Okay. That's the way we're going to do this. Now, do you guys know that change in momentum? You could think of it this way. Final momentum minus initial momentum. That'd be true. Okay? I could rearrange that. You get final momentum is equal to the initial momentum plus the change. Is that true? Okay. And that would be mass of the baseball times its final velocity, which we're solving for, is equal to mass of the baseball times its initial velocity, which was given, plus, I'm going to use a calculus notation here. If you're taking calculus, you'll be familiar with this. Force is a function of time for some time interval. Right? But this is really just the area of F versus T curve. Or I should say the area under force versus time curve. Okay? So let's pop in some numbers. I know the mass of this, let me do a little calculation off screen here to get you guys maximum force. Pick a number that makes sense. That. Okay, let's go maximum force of 1,000 newtons. Okay, is that okay? 1,000 newtons. So see if you guys are following. What is the average force on the baseball? 500. Yeah, okay, you could play off that if that was helpful. Okay. And so average force is 500. Maximum force 1,000. So I got a baseball, 0.15 kilograms. We're trying to figure out what's its post-collision velocity. Okay. 0.15 kilograms here. Okay, now here's where actually there's a little trick. Okay. Remember, momentum is a vector. This is really important. Directions are important. Directions matter. The ball was thrown one way and it's getting kicked back the opposite way. This force is in the direction towards the outfield. So can the throwing velocity be positive or does it have to be negative? Better be negative, like as a velocity value, right? Okay. Did you guys go back to the starting value if you guys are taking notes and make this number negative? Okay. It might be listed in print as just like, oh, the speed was 30 meters per second. You have to figure out, I know the velocity is negative, right? Okay. So I'm going to pop in right here, negative 30 meters per second. So the speed's in here, 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 okay. Then plus, okay. And then the area of this curve. Area under the curve, isn't the area of a triangle 1/2 base height? Or if you want to, you can just say average force times time interval. Either way, okay? I'll do the triangle version. 1/2 times the base of 20 milliseconds. You guys see I have 20 divided by 1,000 seconds, right? 20 milliseconds. Okay. Because if this axis was labeled in milliseconds, could you divide by 1,000 to get it in terms of seconds? You figure that out, right? Just like I did right here. Okay. Times a maximum force of 1,000 newtons. Oh, actually, that's really nice because that 1,000 cancels out that 1,000. So it's that too. Okay. So, clean this up a little bit. 0.15 kilograms times V final equals, let's see, 0.15 by 30. Look at that, negative 4.5 kilogram meter per second plus 1/2 times 20 on 1,000 times 1,000. Okay, this is 10 kilogram meter per second. Okay. So the difference here looks like 5.5 kilogram meter per second. So take 5.5, divide by the mass of the ball, 0.15 kilograms. I'm getting final velocity of 36.7 meters per second. And it's positive because it's headed towards the outfield, and we define that direction as being the positive direction. Okay. Guess what that? All right, that is all the momentum I want to do with guys. Let's head on to the next section, work and energy. In physics, work is defined at work. Work is defined as what times what?
Force times distance.
Exactly, force times distance. Now this is a dot product, which means that only the parallel components matter. Also, dot products give you scalar values. Okay? Now that's to contrast this with something like torque that at a glance might look pretty similar, because R cross F, like, hey, R, that's kind of like distance and force, right? But that's a totally different concept, right? Because that's a cross product, which gives you vector values, and you want the perpendicular components. That's not work. Work is parallel components for dot product, and that results in scalar values. Some number of joules, right? Work is an energy transfer. If Nelly Newton pushes with twice the force for twice the distance, let's call this work naught, and then maybe we've got some new work, work sub 2. If you push with twice the force for twice the distance, guys, that's how many times the work? 4. 4 times the original FD. So that's 4 times the original work. Okay, so power is defined as, see, power, what per what? Work per time. Okay. Remember, power is a rate of work. Okay. Guys, work is measured in joules. Time is measured in seconds. What's power measured in? Watts. You guys remember watts? Okay. Look on a light bulb, it might say 40 watts. That means it's pulling 40 joules per second off the grid. The amount of potential energy possessed by an elevated object is equal to, just from these multiple choice answers, there's only one that's even possible in terms of units. Potential energy, that's measured in joules, power is in watts, distance is in meters, force is in newtons, work, that's in joules, and acceleration is in meters per second squared. So from that you can get, but I'll show you guys more specifically why this is still true. Okay. Suppose you have a crate. This crate has some mass and some weight. Mass M, let's say, has some weight mg. Okay. And you want to lift this crate. Would you have to apply a lifting force at least equal to the weight? Think you're lifting at a constant velocity. That would be the free body diagram, wouldn't it? And what if you want to lift this crate and put it on the shelf? That's so many meters tall. That would be h, right? So I know the work that I would do lifting that crate, because I'd be transferring some energy into it, that'd be my lifting force times the distance. And the lifting force, well, that's just at least as big as the weight of the crate. Okay. And the distance that I move it, wouldn't that be called height h? Oh, hey, mgh. What's that a formula for? Potential energy. Remember, we've been calling this capital U. Okay. Potential energy U is mgh. Okay, so the work you do lifting something is equal to the potential energy that you end up giving it when it's sitting on the shelf. How much further will a car traveling? Oh, there's a little typo here. 100 kilometers per second would literally make it fly off the face of the earth. But let's pretend it says 100 kilometers per hour, which is about 60 miles per hour. Skid compared to one going half that speed. That's the important detail, is that if you double the speed, if you double your speed, what happens to your braking distance? And it doesn't double, it increases by a factor of what? Bohr 4 times. Okay? Show you guys two perspectives on why. One is that here's one perspective. Part has some mass, has some v naught initial velocity. There's breaks to a stop, and some distance d. Okay? Now I'm going to set up something that at a glance might look like conservation of energy, sum of energy initial. I'm going to leave a big little space though. Equals sum of energy final. Conservation of energy is all fine and good for a closed system. But what if we have a system that consists of only the car? And if that's true, then what I would say is that I would want to include the work done by friction. You could say plus or minus. Maybe I'll just go ahead and slap in a negative right here. Work done by friction. This car starts off with what kind of energy? Kinetic, 1/2 mv squared. Work done by friction, isn't that friction force times stopping distance? So if you had a question about like what's the stopping distance, and then at the very end, well, it has no potential energy because it hasn't gone up any hills. It has no kinetic energy because it stopped. The final is 0 meters per second. So it has no energy, no mechanical energy. Right? There's no springs. So whatever kinetic energy that it started with, all gets routed into the work done by friction, force times distance. Now the mass of the car is whatever it is, that's a constant value. The friction force is proportional to that, so that also doesn't change. So what if you're looking at how does the initial velocity, right as the guy was about to hit the brakes, affect the stopping distance? And here's where that squared relationship kicks in. So if you double your speed, what's a factor of 2 squared? 4. So if you double your speed, you have 4 times the energy, and that is all going to get routed into 4 times the distance. What if you triple your speed? 3 squared is 9. That would be 9 times the stopping distance. But I wanted to show you guys another perspective on this too. I'm actually going to leave energy and go back to kinematic motion, which is some of the first stuff that we did way back in the day. Let's look at velocity versus time. Okay? Now, time you pretty much never see when we're talking about energy, so that's a hint that sort of left the energy context. Okay? But so initial velocity, and then this car's going to brake to a stop. It's going to take some time to do that, but wouldn't this area represent the stopping distance, d, stopping distance, right? Is that true? Under velocity versus time curve. Now let's go back to the beginning. Pump up this velocity to twice its original value. Car brakes to a stop. Notice I gave the car the exact same acceleration. The slope is the same. Is that true? Same acceleration. Okay. Might take twice the time to stop. Right? It still takes double the time. But look at the area of that big triangle compared to the area of the original small triangle. How many small triangles can you guys fit in that big triangle? You guys see 4? Well, that's 4 times the braking distance, isn't it? Okay. Another perspective on that. A pendulum swings back and forth. All right, let's check out this pendulum. So, get a vertical line here. This pendulum. There's its motion. There's some mass here. And swinging back and forth. Now, if you knew this length and this angle, the starting angle, do you guys think you could calculate what the height change of this is going to be? Let's say from its very lowest point down here to the highest point at the ends. Call it some delta H, some height change. You guys could do that, right? For the geometry. I think near the beginning of class tomorrow, I'm going to have you guys solve this, but for now, let's just do this question. Okay. Guys, at the end point, it's all what kind of energy? Potential energy, MGH. This mass times this gravity field times this height change, based on the cell and the theta, you have to do that. Okay. That's 100% potential energy. At the bottom, if you define this line as height 0, it's all what kind of energy? Kinetic, 1/2 mv squared. And because energy is conserved, is that number of joules equal to this number of joules? Yep. You could equate those two. You could solve for V. I bet V would equal the square root of 2gh, because it always is, right? For scenarios like that. When a car's speed triples its kinetic energy, I'm sorry, let me go back and fill in the rest of this. Okay, so at the endpoints, energy is all potential, bing. At the lowest point, it's all kinetic, bing. Kinetic is transformed to potential. Potential is transformed to kinetic. Bing, bing. That's all look good. When a car's speed triples its kinetic energy, because if you throw a factor of 3 on this initial velocity, the kinetic energy goes up by a factor of 9, because 3 squared is 9, right? It would also be 9 times the braking distance, too. If the velocity of a moving object doubles, what else also doubles? Let's go through part by part. Acceleration. Well, acceleration is a rate change of velocity, so that doesn't really get to this question. You need a time interval. That doesn't really help. Kinetic energy. What was the formula for kinetic energy? Kinetic energy is 1/2 mv squared. So if you double this velocity, then kinetic energy increases by a factor of 4, which is not doubling. Okay, so it's not kinetic energy. Momentum. Hey, momentum. Wasn't that mass times velocity? And if you double the velocity, that's got to be it. If you double the velocity, you double the momentum. Okay. Any relationship? Patrick? Is there? A simple machine works on the principle that this one is work input equals work output. So let's go through one of the simple machines that you guys did for one of your labs, which is a pulley system. There's also levers, there's gear systems. Those can give you mechanical advantage. Let's look at, let's say a pulley system that looks like this. Okay. I'll have a single fixed pulley right here. It's fixed in place. I'll have a single movable pulley right here. It's free to move up and down. This one's attached to, let's say, some weight. And I've got a guy over here pulling, say, some input force trying to lift that thing, right? Got a floor down here. Let's say that this weight right here is 200 newtons. 200 newtons. Let's say the pulleys themselves are frictionless, massless, and so they're just Hey, do you guys see what is the tension in the string right here? 100 newtons. Same story here, right? Hey, it's kind of like the weight got split 2 ways. Okay? In fact, if you look at the movable pulley, you can pretty quickly figure out what the mechanical advantage is. Because what's the force that this guy's pulling with over here? 100 newtons. 100 newtons of input force to lift a 200 newton weight. Okay? I mean, if this guy, maybe this is maximum pulling force. I can only pull 100 newtons. That's my breaking point. He can lift something that's twice as heavy as he'd normally be able to lift using his pulley system. You guys see his mechanical advantage is 2 to 1. Okay? Force output compared to force input. Okay? But he doesn't get something for nothing, even though he's amplifying his strength. Is he amplifying the amount of energy in the system? No, because energy is conserved. You can't amplify energy. It'd be nice if you could. You could run the entire world's electric grid on a single lump of coal, but doesn't quite work that way. Yeah, so here's the sum of energy initial equals sum of energy final. Maybe sort of go back to that context. Work in equals work out. That's the answer to that multiple choice question. Force in times distance in equals force out times distance out. Okay, so even though he's twice as strong, he only needs 100 newtons in to get 200 newtons out. 100 newtons in to get 200 newtons out. Output force. Suppose he wants to lift this thing 1 meter. Really want to lift that weight 1 meter. How much rope does he have to pull? 2 meters. So that's how he's paying for it. He's paying for it with the distance he pulls. Okay? Is that? How many joules of work done on a box? Force of 25 newtons, pushing it for 3 meters. So work equals force times distance. So if you have a force of 25 newtons, you're pushing it for 3 meters. You see 75 joules of work. How much power to do 40 joules of work in 5 seconds? So power is work per time. So if you do 40 joules of work all in 5 seconds, wouldn't that be like 8 watts of power, 8 joules per second, 8 watts. Oh, you know what? I forgot to remind you guys about power. Let me go back to the setup right here. Power is work per time, right? Power is a rate of work, right? Now, this is sort of the definition, right? So this ratio, okay? Joules per second. They give you some number of watts. Okay? But let me dig into this a little bit more. You guys remember work is force times distance divided by some time t, like that, right? Okay. Now, of course, you could combine those and just go back a step, get that again. But you could also combine these variables a little bit differently. Look at this right here, distance over time. Force times velocity. You guys remember that one? Okay. Now, this formula right here, I'll tell you guys, this might be useful, for example, maybe if there's an elevator being pulled up by a cable at some speed, and you know the tension in the elevator cable, and you know how fast the elevator is moving at that moment, you could calculate how many watts of power the motor at the top is pulling off the grid to pull up the elevator. Okay. The tension times the instantaneous speed of the elevator. You do that. Okay. That might be where that would be useful. I'll tell you what else is that this is not on AP's equation bank. So this one might be a good idea to memorize and just pull in your back pocket. And there could be a question that this could help you guys out on the exam too. All right. All right. Let's do this. Let's do one more and then we'll be done to double check. I'm pretty sure you guys don't have the VTV news. No, I don't see one. Okay, so we'll do one more question and then for the day. All right, let's do, there's a cliff. And I'm going to drop this ball off this cliff. And I'd like to know, what is this crash speed, VF, at the bottom of the cliff? I'll tell you the cliff is height 100 meters tall. 100 meter tall cliff. Okay, and let's say we're on Earth. Okay, so gravity field is about 10 meters per second squared. Okay. See who gets this first. Who can tell me what is the crash speed of that ball? Release from rest. Just drop that ball. How fast is it crashing into that dirt? Oh, you know what? I think that was about the ring, so just solve this with you guys. Okay, you can either do this, df squared equals v naught squared plus 2ax. Solve for it that way. Or you can do conservation of energy. Sum of energy at the top in GH equals sum of energy at the bottom, 1/2 mv squared. Okay, and solve for it that way. You'll always get this. Whether either one you use, you'll get v final square root 2gh, and that works out to be 44.7 meters per second for that particular cliff height. Okay. All right, so tomorrow we'll wrap up some energy stuff with you guys, and then we'll move on to next part of that review. You guys all turned your quiz in? You guys have a good Monday.